I know.
Hey, Rocco, you want a giant shrimp? How am I supposed to use words in this sentence?
All right, so there's 3 more things that we need to talk about to finish up 11.5. We're going to look at one more domain problem just to remind ourselves what we were doing with domain. We really only did one problem last time. We're also going to sketch curves and then talk about limits and continuity. And then in section 6, we'll talk about derivatives and antiderivatives. Okay. So we started talking about vector valued functions last time. These are vectors, but they have functions of t as their components. All of the vectors that we have been dealing with up to this point have had constants as the components or scalars as the components. And so far what we've talked about is the domain. The domain for the vector valued function r of t, we said is going to be the intersection for the domain of the individual functions. So we've got to find the domain for our individual functions the same way we would have found domain in algebra class, and then see what they all have in common. Because if we pick a t value to plug in, it's got to work in all 3 pieces. We don't want any of the pieces to come out undefined. Intersection, sorry, that's one word. I put a awkward space in there. So we reviewed last time the rules for finding domain, and these go all the way back to Math 171, pre-calculus algebra, finding domain of different types of functions. Radical functions, rational functions, logarithmic functions, things like that. Basically what we're looking for are problems. It's easier to look for problems because that list is smaller. And if we don't see any of the problem functions, that means we can use anything. And then for the domain for r of t, we pull all those problems together and write interval notation for the set of numbers that addresses all the problems. So I want to look at one more example really quick for domain, and then we're going to go on to sketching. No, all good. It's gonna work. So we're looking at them individually. Arturo, what'd you say about the first one?
Well, I thought that anything can go first.
Right, no problems with the first one. It's just a polynomial, it's a quadratic function. No problems. We can use anything we want. We've already done a domain problem. I just was gonna do another one real quick.
Was it the same like problem?
Nope, it was a little bit different.
It's just you can't use one on the chart. It's got really bad data. 1 or 0.
You can't use 1 or 0 on that one. We don't want the denominator equal 0. So we say t squared minus t can't be 0. And if you factor it, they've got a t in common. So t can't be 0. T minus 1 can't be 0. So t can't be 1. T can't be 1 or 0. I don't think we had a log in our other example. I think we had we had an e, a radical, and a rational. There are certain numbers that we cannot take the log of. We can't take the log of negatives. We can't take the log of 0. We can take the log of a positive number. So we just need to make sure that t minus 2 always comes out positive. So algebraically, the way that we write this and what we're going to solve is t minus 2 must be greater than 0. So t must be greater than 2. And we want to take all of this stuff and put it together. You don't have to. For me personally, when you've got several different components to the answer, sometimes it's easier to see what the answer is going to be if you do. I like to draw the number line and throw it all in a number line. Whoops. Stop. There we go. Bless you. All right, so f of t has no problems. We can use everything. G of t, we've got to throw out 0 and 1. But we can be everything less than 0. We can be everything in between 0 and 1. And we can be everything bigger than 1, according to G of t. And then for H of t, we've got to be strictly greater than 2. The domain for R of t is only where all 3 of them overlap. So only the section that got, or sections that got shaded 3 times. Nope. It does, I'm sorry.
It's green. It'd be like greater than 2, wouldn't it?
It is greater than 2.
Yeah.
Mm-hmm. So let me do this in purple. Is that better?
Sorry,
So the only piece that got shaded 3 times is the 2 to infinity. Does 2 get a bracket or a parenthesis?
Parentheses.
It gets a parenthesis. Because if you look back at where we got to, it says strictly greater than, and if you look how we marked 2 on the number line, it's an open circle. So the capital D with a little subscript R, that just means the domain for the function R. Doesn't matter how you write that, as long as you've got 2 to infinity. So I just wanted to show you a second example of that. So drawing these can be really neat. Drawing them in 3 dimensions is kind of tricky, but drawing the 2-dimensional ones is kind of neat. No, I don't want to do an example. No, we're sketching the curves. Sketching the curves that these vector valued functions create. Yes. Section 6 is derivatives and antiderivatives.
First calculus.
They're actually really easy. That's our first bit of calculus. We actually have limits here at the end of this section.
Is this not like piecewise function? No.
Piecewise function, we only use each piece at specific spots. But for this one, we're using all 3 all the time. They just, right, we're always using all 3. They just say what's going on from a different perspective. So the X is telling us what's going on in the X direction. The Y is telling us what's going on in the Y direction. The Z tells us what's going on in the Z direction. So all of them are always being used.
So now this is art class.
Just a little. I won't judge your artistic abilities.
I think me and Adam really making on CAD or drawing. What?
You can use CAD.
I haven't actually learned that. Computer aided design. I think we're putting an astronaut at the other name now. Yeah, you get my government benefits.
One way that we can approach this is we can substitute values in for the parameter. Most of the time t is used as the parameter. There are some situations where our vector valued function has trigonometry in it, so you might see theta for the parameter. We can just plug values in for the parameter, and it's going to tell us points on our curve. And we can plot points. That's not always the best way to do it, but it works. Another option is to eliminate the parameter. If you're in 2 dimensions, you can eliminate the parameter and find the equivalent rectangular equation. This gets a little trickier when you're in 3 dimensions, but it's pretty easy in 2 dimensions. What side is that? Interesting.
Bad about it, too. You blame plots for this, It's the first time those words have ever been used. Trump and truth. Unless Trump doesn't say truth, unless that's the sentence.
People, I think, said they started writing something.
He's talking in Mexico, right?
What are you talking about?
Mexico's gonna take the United States like to union court or something like that.
It's a little fun about it. Mexico doesn't want
Yeah, you know,
We're going to sketch a graph of the vector valued function r of t equals 1/2 t radical t minus 2. And we're actually going to do this both ways, so I can show you that both ways work. First of all, what t values do we need to stick with? We can't just plug in any t value that we want to. Can I start with t equals 0? One of the...
No,
Why not?
because the square root
We get square root of -2, right.
is gonna be greater than or equal to 2.
We have to use t values greater than or equal to -2. That's the domain for this vector valued function. Greater than or equal to 2.
So
Yes.
we're still using the previous domain?
Huh?
We're still using the previous domain?
The other one was strictly greater than 2 because it was natural log of t minus 2. So for this one, the domain is 2 to infinity. So that's an important thing to recognize when you start the problem, because you don't want to plug in t values that are not going to give you a point back on the curve. So you can make a little chart. Doesn't have to be a chart, but it keeps it nice and organized. If I plug in t equals 2, what do I get for my x and y component?
That would be 1 for the x.
1 for the x,
0.
0 for the y. I am not going to plug in 3.
We get 6.
Anybody have any idea why I'm not going to plug in 3?
You don't know the square root. Like,
I do know the square root of
you
1.
do the square root of 1. Because 1/2 of 3 is.
I don't want to plot decimals. Yeah, I don't want to plot 3/2. Okay. So we could plug in 4.
But then you get this.
But then we get square root of 2.
Point 6.
So Adam says plug in 6.
16.
So if I plug in 6, half of 6 is 3. 6 minus 2 is 4. Square root of 4 is 2. I don't want to plug in 16.
18.
Right, we're going to plug in 18. It's okay. Yeah, minus 2. I'm going to plug in 18 next. Half of 18 is 9. 18 minus 2 is 16. Square root of 16 is 4. That's probably enough to give us an idea of what this graph looks like.
38.
Yeah, we can write it if you want to. 38 would be another good number that would give us whole coordinates. If we plug in 38, half of that's 19. Minus 2 is 36. Square root is 6. So we've got 1, 0, 3, 2, 9, 4. It's not a straight line because the slope from 1, 0 to 3, 2 is not the same as the slope from 3, 2 to 9, 4. It is a curve. Yes, there is. And that would be to eliminate the parameter and change it to a rectangular equation. There's still a little bit of work you need to do on paper first. So this first point corresponds to our t equals 2. That's the start of our domain. The second point corresponded to t equals 6. That third point was t equals 18. There's one more thing that we need to draw on this graph, and that is the orientation of the graph. Remember, this is a vector-valued function. So there is a direction associated with this graph, and the direction is called the orientation. So we want to indicate what direction these points are moving in. The orientation of the graph indicates the direction of increasing values of t. Since technically this is a graph of a vector-valued function, direction is required. On this one, it's not that big of a deal because it has a fixed starting point. But if our domain was all real numbers and it can go forever in both directions, we wouldn't want an arrow at both ends. We would want arrows only pointing in one direction. So we could get an idea of what the graph looks like just by finding those points, just by plugging in values for the parameter figuring out what the x and the y are that go with it and plotting the points and connecting them. You have to have a general idea of the shape of the graph ahead of time in order to plot them and connect them correctly. Another option, though, is to take the x component and take the y component and eliminate the t and turn it just into an x equation and a y equation. If you remember back to when we talked about parametric equations for a line, we said that first piece was equal to x and the second piece was equal to y. And we could write them as parametric equations, or we could write them as a vector. And we could do the same thing here. So we had r of t equals 1/2 t, and we had square root of t minus 2. We could write this as a set of parametric equations as x equals 1/2 t, y equals square root of t minus 2, and use algebra to get rid of the t's. Think of it as a system of equations and eliminate the t. So we're going to solve one of them for t and use it to replace the t in the other one. We're going to solve one of the equations for t. We prefer to solve the x if possible, and then that will leave our final answer as y equals a function of x, which is how we're used to seeing equations that we graph on the xy plane. So if we solve the x equation for t, we get t equals 2x. And then I can take the t in my y equation and replace it with 2x. It's the same exact t in both equations. And what we're left with is y equals the square root of 2x minus 2. And that we can plug in our calculator to see the graph. So at that point, Joe, we can use our calculator. So there's still a little bit of work we've got to do by hand. If we look at that graph and we look at the points on that graph, it should match up with what we did the first time around. Just from the standard viewing window, I do see it goes through the point 1, 0, just like ours does. And then if I look at the table, it goes through 3, 2. Did we have 3, 2? Yep, we had 3, 2. And it goes through 9, 4. Goes through 19, 6. Yep. Same graph. So the first method is a more numerical approach. The second method is a more algebra approach. This one is a little bit different. The numerical approach is similar, but the algebra approach is different because you'll see it's not algebra. It's not calculus.
No, it's trigonometry.
It's
I
trigonometry.
hate trigonometry. Why?
That is blasphemy. You can't hate trigonometry. And now you love it.
Still hate it.
Trigonometry is like probably one of my.
Once you start tutoring math, things like start making more sense.
It's so easy. Dang it,
Mhm.
you got it on.
I never even touched trig. I touched it a little bit pre-calc, so, you know,
No, you need like a full, intense course of nothing but trigonometry.
I wish I had it, but they don't offer
I
that
don't
course
understand
anymore.
why trig wasn't a math class before at Southern.
It's because integrated math took it out.
Mhm.
Terrible.
It's because the Common Core and integrated math, they took out a specific trig class.
Like trigonometry seems like a huge like section of math.
There are
that you
advanced
need to know.
models of physics,
Yeah.
advanced models.
But instead
No,
of
advanced
learning, like,
functioning models. I don't know.
imaginary stuff and just algebra, get it under even the already kind of go.
They teach algebra for 3 years now instead.
Like trig is more useful.
So they're beating the dead horse there.
Yes.
So the only thing I remember about geometry is just a ton of area equations that now I just look up on my phone.
And usually they just give you. Oh, I was like, what is WS?
WS.
What is WS thing? It's a code.
Oh, cosine. Sorry.
Or it looks like that.
Omega.
Yeah. Physics.
Angular velocity.
Yeah.
W is angular velocity. Yeah. Sorry, cosine theta. Angular velocity times arc length times angle. I'm sure it means something. So if we do this one numerically, we're going to do it similar. But if we want to do it algebraically, we're going to do it a little bit different. So numerically, we said we're just going to plug in values for the parameter. This time the parameter is an angle inside of a trig function. And we want to make sure we plug in values that make sense and that are going to give us a nice number back. We don't want to have to try to plot crazy decimals. Okay? We want to plot some nice whole numbers. So I'm just going to do multiples of pi over 2. So I'm going to start with 0 and do pi over 2, pi, 3 pi over 2. We'll see what that gets us so far. These are just unit circle values. And then there's a times 4 in the front. So for the x, we want cosine of 0. Should be 4, yep. And then sine of 0 is 0. For pi over 2, we get 0, 4. Over at pi is over on the negative x-axis. We get negative 4, 0. 0, negative 4. Yeah, let's see what we got so far here. So here's 4, 0. Here's 0, 4. Here's negative 4, 0. Here's 0, negative 4. We are going counterclockwise around a circle of radius 4. Counterclockwise around a circle of radius 4. That's a pretty good circle, isn't it?
Let's see what it's-
I actually could have used the circle function up here since I've got the computer. Maybe it's looking down the top of a tornado.
It's not quite an oval. So it's like a couple of racetracks.
Are there any circle racetracks?
They're all ovals. mostly.
Yeah.
There's one
Or
triangle.
road.
There's one triangle, and there's two road courses.
I grew up right outside of Watkins Glen.
I've been by the sign that said Watkins Glen, this exit, and that's about it. I can't remember where we stopped at, but it was somewhere there when we stopped at ice cream. It's pretty good.
That is one thing that nobody you can't find down here is like roadside ice cream stands. I don't know, but yeah, it's like in a trailer though. Like in New York, yeah, in New York, every few miles, oh, it's like a shaved ice or something. In New York, every few miles, there's like a soft serve ice cream stand.
Well, if you walk through a few miles in this direction, you run into a field.
No, not a gas station. We got gas stations too.
I wish I could remember where it was at. Because we were on our way to Niagara Falls.
All right, so that is the numeric method. So you've got to pick your values appropriately based on, we are going to do, but we're going to do it differently. We're not going to do the way we said earlier, where you solve for one and plug it into the other. If we want to solve for theta in one of these equations, we're going to pull them out, like we said, x equals 4 cosine theta, y equals 4 sine theta. If I wanted to solve for theta, what function are we going to end up with? What kind of function? Inverse trig. You want to plug inverse trig into another trig function? I don't want to. I prefer not to, if I don't have to. There's another way to do this. What we're going to do is we're going to solve these equations for sine and cosine. We're going to isolate the sine and the cosine. And we're going to use a trig identity. Okay? Nope. Nope. So if I solve this for cosine theta, I get x over 4. If I solve this one for sine theta, I get y over 4. There is a trig identity that tells me a way that I can combine sine and cosine.
Oh, is it the cosine squared plus sine squared?
Cosine squared plus sine squared equals 1. Our Pythagorean identity. Well, cosine is equal to x over 4, so I can replace cosine with x over 4. So this is going to be x over 4 squared. And sine is equal to y over 4. So I can replace sine with y over 4 and have y over 4 squared. So this is x squared over 16 plus y squared over 16 equals 1. But since they have the same denominator, I'm going to multiply everything by 16 and get x squared plus y squared equals 16. That is the equation for a circle that is centered at the origin with a radius of 4. You just have to know what to do. If it's trig, you just have to know what to do with it. Use the Pythagorean identity. We've got Pythagorean identities for tangent, secant, cosecant, and cotangent as well. So if for some reason they gave you tangents and secants, then use a different Pythagorean identity. Yes. Yep, that 4 that we see in front is the radius. If they had different coefficients, If they gave us tangent, we would just use a different Pythagorean identity. And it would turn into a different graph. And I think it would end up being a hyperbola.
So if we calculate y equals square root of 60 plus 60.
You would have to do plus and minus. If we wanted to solve that for y, you'd have to, and when you do the square root, you gotta put plus or minus in front of it. So you'd have to put both of them in. There is a circle graphing function on your calculator if you know it's a circle. Under draw. But you'd have to know it's a circle ahead of time. Under draw option 9. You just have to type in 0, 0, 4. The first two numbers are the center, and the last number is the radius. And it will draw a circle of radius 4 for you. Otherwise, if you're going to use the y equals, you have to type in the top half and the bottom half separately, because a circle is not a function, doesn't pass our vertical line test. And the y equals will only graph functions. So most of our algebraic functions we can solve for t and use it to replace in the other, but the trigonometric ones, we want to approach this way. We want to use our trig identities to help us combine them. That way we don't have to do any inverse trig. This helps us avoid the inverse trig. And don't forget, when you draw that circle, you've got to put your arrows. There is a way that we could reassign the sines and the cosines and make it go clockwise instead. So the way that they have them, this thing does go counterclockwise. And that's important. So we just got done doing 2 examples where we changed a vector valued function into a regular rectangular equation. We're going to do that in reverse now. We're going to take a regular rectangular equation and turn it into a vector valued function. And actually this way is easier. The reason this one is easier because in a rectangular equation, the variable x is the independent variable. That means we can assign it to be anything we want. So the easiest way to do this is to let x be equal to t. And then if x is equal to t, we can replace x with t, and then we'll have our y equation in terms of t. And then from there, we just have to separate the 2 pieces and write them as our x component and our y component as a vector valued function. Assigning x to be something other than t wouldn't change the curve. It would just change how fast or how slowly we go through the points on the curve. So right now, it's like a one-to-one correspondence. When t is 1, x is 1. When t is 2, x is 2. When t is 3, x is 3. So if we wanted to go through those x points quicker, we could say that x is equal to, how can we go through those x points quicker? Would we want to put a large coefficient in front of t or a small coefficient in front of t? A large one?
Small. Huge.
Start small.
All right, so let's do an example then. Anytime you're not sure, just do an example with real numbers and see what happens. So if we wanted to go through the x values quickly, so I wanted my x value to get large quickly, we would, no, not gonna do exponents. So, well, we could actually, we could. If we let x equal 5t, if we plug in t equals 1, then x equals 5. And then when t equals 2, x equals 10. So yeah, that's going to go through the x values much quicker. So if we put a large coefficient in front of t, it's still going to go through the same x values, it's just going to go through them much quicker. If we want to go through those x and y values slower, we could put a fraction in front of t, like a half or a quarter or a tenth. And it will still follow the same curve. It'll just go through the points a lot slower. So we're going to convert y equals x squared minus 3x to a vector valued function. So this is a parabola. The easiest thing to do, if they don't give you any stipulations, the easiest thing to do is say x equals t. And if x equals t, that means y equals t squared minus 3t. Simple. So the vector valued function, so this right here is just a set of parametric equations. Don't stop there, because they asked for a vector valued function. So r of t equals t comma t squared minus 3t. Or you could write it with the I and the J.
If you did it with I and J, would you do minus t squared, or would you just keep it positive?
It would be a plus, and then you'd have to have parentheses around your t squared minus 3t. So you'd say ti plus parentheses t squared minus 3t j. If your component has multiple terms, I always do plus and put it in parentheses. If it's a single term and it's negative, then I'll sometimes put minus. But if it's multiple terms, I always do plus and put it in parentheses. Because we don't want just the sign of the first term to dictate the sign of everything. Because it's only the sign of the first term. All right, this one's harder, but think about what we did with the circle earlier. Anybody remember from Calculus 2 what that shape is? It's an ellipse. Gold star for Joa.
It's not a circle. I can't even
Right.
if it makes sense for size symbols.
Right. It's not a circle because the denominators don't match, but everything else about it's screaming circle.
What do you mean Calc 2?
It's the end of Calc 2. We talked about these conic sections.
We never talk about conic sections.
This isn't Calc 2.
Did we not
I
talk?
think it was at the beginning. I thought it was at the beginning.
I don't remember talking about conic sections.
I swear to,
We do I did conic sections in pre-cal.
I still have my notes right here.
I swear right at the beginning of chapter 10.
We never did chapter 2.
Yes, we did.
No, we only got a chapter 9.
No.
We didn't have a test on chapter 10.
Oh, was it a day you were absent?
I was never absent.
Yes, you
I
were.
was here every single day. I was here every single day.
Tyler's got his notes. We did some of chapter 10.
Well, last. We were talking about.
No, we only got chapter 9.
Did we go over ellipses?
Told you. The last thing we did were those funny names. There's 2 funny name things with the series.
The Taylor.
The Taylor polynomials and the McLaurin polynomial.
Yeah.
That's the
We
last
did
thing we
nothing from chapter 10.
did. No, we skipped chapter 10. So I'm gonna fail when I take my validation test.
No, you're not.
I did conic section.
No, because everything in chapter 10, everything that's important, we'll cover in here.
Yeah, excuse me, I haven't done this since
Because
pre-cal.
we ran out of time before you were out there too.
Oh, yeah.
Like a month.
Something in Calc 1.
Altogether, it was like a month straight.
Okay, so everything about this is screaming circle. The x squared plus y squared equals r squared. The problem is, if you look back at the problem we did earlier, where they have the same denominator, so we said we can multiply it over. This one, they don't have the same denominator. So we can't just multiply it over. And because they don't have the same denominator, that means when we graph it, we're gonna go a different distance horizontally than we do vertically. And that's what makes it the ellipse shape. Because there's a different horizontal distance than there is a vertical distance. It's all good.
Why are you staring? What's good?
Everything. I said it's all good.
I know. Why? That's random.
All right, what did we do earlier to get our answer into this form? Trig identity, okay? Let's reverse that. Anti-trig identities. Let's anti-trig identify this. All right, what trig identity? Pythagorean. Okay, there's 3 of them. Which one equals 1? There's only one trig identity where a sum equals 1. Yep. So this is going to match up with, I like to do cosine squared first. We're going to try to match these guys up. Cosine squared plus sine squared equals 1. That is a trig identity. Our equation says x squared over 9 plus y squared over 25 equals 1. So let's start pairing up some pieces.
3 plus y is a r.
We're going to do one more thing here. Because if we want to change it to a vector valued function, we want to know what x equals 1, know what y equals. So there's one more algebra step on the cosine theta equals x over 3.
You want to know what cosine equals?
No, we want to know what x equals.
Oh, you
3
multiply 3
cosine theta.
X equals 3 cosine theta. And then sine squared
We just skip it and say 25.
Yeah. So now we've got y equals 5 sine theta. So we've got our two components. We were asked to write a vector valued function, so we need to write it as a vector. So r of theta, we're using theta here as the parameter, is 3 cosine theta I plus 5 sine theta j. So when those coefficients match, it makes a circle. When those coefficients don't match, it makes an ellipse. So the one we saw earlier, they were both 4s. And we converted it, it turned into a circle of radius 4.
So that would be equal. Length of it.
Mm-hmm. Yep, it's because we go 4 horizontally and 4 vertically. So it's the same distance in every direction, and that's the definition for a circle. This one, it's 3 horizontally and 5 vertically. So it's taller than it is wide. So it's that oblong shape, which is the ellipse. So again, the trig has to be done a little bit differently. You've got to use the identities to help you along. If it's algebraic, just let x equal t and then replace it. Right? Yep.
So usually when you're doing trig, cosine represents by x.
Yes.
But when you first learn trig, you teach sine first.
Yes.
I feel like that's
I mean, what we're always going to talk about.
SOHCAHTOA. Right. This.
Trig's not used to that way.
That's true. It's always sine first, cosine second when we learn things.
because it's just easier to put it first.
Mm-hmm.
So good.
And it probably is because on a graph, sine uses y. And we usually, if we're changing it to an algebraic equation, we want y equals a function of x. Maybe that's why.
Because so Toa sounds weird.
COSATOA.
It's kind of hard to say. Cosatoa.
Well, it would be CASOTOA.
Yeah,
CASOTOA.
Cosatoa.
It makes more sense. And a lot of other things would probably run smoother if cosine was first. Mm-hmm. And when we write the Pythagorean identity, they always give it to us in the book as sine squared plus cosine squared equals 1. But anytime I use it, especially in these types of problems, I always write cosine first because I want cosine to equal x.
When we do cosine is x and y.
Uh-huh. Yep, the points in the unit circle, cosine is x and sine is y.
That's what
The first one's sine because we always do sine. We always learn about sine first and cosine second. Yeah. Yep. That is a good point, Ethan. I might start teaching it differently. But then I need a textbook to go along. The problem is the textbooks.
I don't know.
I'm not allowed to advise people not to buy the textbooks.
Of course.
Are you allowed to not berate students for not playing?
Seriously.
I'm not allowed to berate students, period.
I'm like 2 weeks away from just watching my
You have to get there, you can't do that. Get it right now.
Well, even on time.
I don't have to be there right at 3.
You're testing. You get more sleep if you get there. You gotta go. That's what I'm saying. I won't teach the rest of the class. Just leave the notes there.
Yeah, Ethan said he wants to teach.
Just post these notes and I'll teach them.
No.
Let me do limits really fast. Limits are super easy. If you remember them at all from Calculus 1. But these are not going to be crazy limits. These are not going to be crazy limits. They're going to be pretty basic. A vector valued function R of t is continuous at t equals a if R of a is equal to the limit as t approaches a for R of t. What this is saying is the function value and the limit are in agreement. As you approach, the limit tells us what it looks like it's going to. The function value is where it actually is. If those two are in agreement, then it's continuous. If it looks like you're approaching one number, but then all of a sudden there's a jump to a different number, that's a discontinuity. Or if for some reason your limit doesn't exist, that's a discontinuity. So anytime that your function value and your limits exist and are in agreement, your function is continuous. So your actual function value and what it appears like your function value is going to be as you get close. You want those guys to match. It's usually easier to identify discontinuities and then throw them out, kind of like with our domain. It's easier to identify problems in the domain and then throw them away. It's easier to identify discontinuities and throw them away. And these two concepts are actually very closely related. We're going to be working with normal functions here. Nothing crazy. We're not really going to be working with piecewise functions. We're not going to stick a piecewise function into a vector valued function. So if you just think of your normal functions and where they could possibly have discontinuities, a normal function that we have seen probably since pre-calculus algebra that could possibly have a discontinuity is a rational function. It's got asymptotes. So those are places where we have infinite limits. The limit doesn't exist. Also with rational functions, if we're able to factor and cancel something in the denominator, that does not create an asymptote. Does anybody know what that creates?
You what?
If you're able to,
The whole.
it creates a hole. That is a discontinuity as well. And then also you need to take into account the domain. So the square root graph, I don't want to say it's continuous down at -3. It's not even defined down at -3. So you're always going to start with the domain and then work from there. So since this definition involves limits, we need to take a step back and talk about limits real quick. And then we'll do a continuity problem, and then we'll be done. So, like I was telling Adam earlier, we're just working with 3 functions simultaneously. When we were trying to find the domain for the vector valued functions, we just had to consider the domains for our 3 individual functions simultaneously. If we want to do a limit, we just have to do the limit of our 3 individual functions simultaneously. You pretty much treat it as 3 individual limit problems. They're separated with addition and subtraction. Those individual components, the I, J's, and K's, if you write it out in that form, they're separated with addition and subtraction. And back in calculus, we learned that if things are separated with addition and subtraction, we can take the limits, we can do the derivatives, we can do the antiderivatives individually. Which means when we start doing the calculus on these vector valued functions, we're just going to treat each of these components as their own little subproblem. We've just got 3 problems to do, is all. We have to do it for each component. I do not want to use X. Stop what you're doing. I should be using T. What's the first way you should always try to do a limit?
Graph it. Plug in 1.
Avoided alcohol.
Direct substitution.
Yeah, see if it's indeterminate form.
Always just try to plug it in and see what happens. It's called direct substitution. We want the limit as t approaches 1, so we're going to plug in 1.
Well, it's gonna work for everything except, like, it's gonna work for all of them.
Always just try to plug it in. And then we'll see if we run into trouble. But just start with direct substitution, plug it in, see what happens. So this is technically, I'm going to write this out once and only once, and you're never going to see this again, because you don't have to do this. You don't have to write this out. But we're technically doing the limit as t approaches 1 for 2t over t minus 3 I plus the limit as t approaches 1 for sine of pi t j. I don't have room. I make room. Plus the limit as t approaches 1 for t squared plus 1. Okay. It's just 3 problems. We do it once for each component. And it's going to work just fine for all of them. So if we plug in 1, we get, yep, negative 1i, because we get 2 over negative 2. We get sine of pi. What's the sine of pi? 0. You can write 0j if you want to. I'm going to leave it off. I'm going to write it this time. Negative 1i plus 0j. I'll clean it up in a minute. If we plug 1 into t squared plus 1, we get 2k. So if we clean this up a little bit, we got negative I plus 2k. That's our limit. Yep.
Is that you get the resum right?
Almost.
When do we plug in 0?
If it says the limit as t approaches 0. The limit as t approaches 0.
What if we can find the limit? Just by plugging it in.
We're going to do another one. Doing another one. Did I say 1?
She said one bed.
I'm going to rewind the video and see.
Okay, you do that right now. Do it.
Sorry.
And like, what are they on?
I don't know what she's
Probably watches some of it because she got other stuff to do.
Eason?
Yes.
I'm using 0.
It's not cool when you're approaching 0. What you said?
Saying is I should plug in 1.
Don't do it. Don't do it. No.
Okay. Don't make it up, Miss Peacock.
Doc, I don't know. I had this stupid sine 13, sine of 0, sine of 0 is 0, 0 to 0. That's a thing 299.
Easton, what do you get if you plug 0 into the first one? 0 over 0. You get 0 over 0,
1.
which is indeterminate.
So factor out t.
0 over 0 is indeterminate, which means since they're polynomials, it means they have something, a factor in common that can be pulled out and crossed out. Okay? So I'm going to pull a t out of the bottom. It doesn't always equal 1. This one's not going to equal 1.
Well, 0 factorial equals
I'm
1.
saying 0 over 0 should equal 1.
Just set the rule.
Do anything over, so I forgot what it said, it equals 1.
That's true.
Now, all of a sudden,
Now all of a sudden, we're backtracking. So those t's cancel. And once we get rid of the t's, we're left with 2 over t minus 9. And we'll try again.
So negative 2 over 9.
Negative 2 over 9. Mhm. And what do we get if we plug 0 into sine 3t over 2? We get 0. Mhm. Over 2, which is 0, 0j. So the answer is just negative 2/9 psi. Negative 2/9 psi.
Psi?
Also side?
Oh,
Nine-
negative 2/9.
Negative 2
Okay.
ninths.
I was like negative
I.
2/9 psi. What?
Negative 2/9 psi.
it's all-